So the first application I want to consider is singularities. Okay. All right, so let's start off with a motivating example that I believe I showed you, on the first day of class. Okay. So let's take a simple two-link planar manipulator. Okay. And let's write the forward kinematics. Okay, so x1 is L1 C1 plus L2 C12. So we define the angles in the usual way. Here's theta 1, here's theta 2, here's link length L1 and L2. Okay, so x1 is L1 cosine theta 1 plus L2 cosine of theta 1 plus theta 2. Okay, and x2 L1 S1 plus L2 S12. Okay. Now take the Jacobian. Differentiate both sides with respect to t. We get x1 dot, x2 dot. Okay, this is equal to a 2 by 2 matrix. What is that 2 by 2 matrix? Well, it's minus L1 S1 minus L2 S12. And here it's minus L2 S12. Here we have L1 C1 plus L2 C12, L2 C12. So here's the 2 by 2 matrix. Okay, terms are split up that way. Multiplied by theta 1 dot, theta 2 dot. Okay, so here's my Jacobian, right there. Okay. Now let me call this vector v1. Okay, and let me call the second column v2. Okay. All right. So the reason I'm doing that is because I want to be able to write x dot as a linear combination of v1 and v2. Okay, so x dot is now j sub theta times theta dot, okay, which can further be written as v1. Okay, now v1 depends on theta. Okay, so for now, let's remind ourselves of that fact by writing it this way, times theta 1 dot plus v2, again, function of theta, times theta 2 dot. Okay. All right, so let me put the robot in this configuration. Okay, so theta 1 equals 0. Let's say theta 2 equals 90 degrees, pi over 2. Let's see what x dot looks like. So let's see what v1 and v2 look like when theta 1 is 0 and theta 2 equals 90 degrees. I believe this, so theta 1 is 0. So the signs, that's 0. Theta 2 is 90 degrees. So it's, what is that? It's minus L2 is left here. Down here, theta 1 is 0. So L1 is here. L2 cosine of 90 degrees, 0. So pretend L1 and L2 are, say, 1. So we have, let's see, minus 1 here. Okay, theta 1 is 0, so L1. So it looks like minus 1, 1, right? So maybe v1 points in this direction. Okay, and v2 points in which direction? 0 cosine of sine of minus 8. So it looks like it's just, let's call this v1. v2 looks like it just points in the this direction. Is that correct? Something like that? Okay. So in this configuration, v1 and v2 point that way. How about that configuration? All right, I'm not going to do the calculation, but I figure it's going to be some, I don't know, something. Okay. What if we extend it out completely? V1 points in that direction. V2 also points in the same direction. Okay, same direction. So V1 and V2 tell you in which directions the tip can move. Okay, so here the tip can move in any direction spanned by V1 and V2. So that's the entire plane. Here too. Okay, here V1 and V2 line up. Okay, so that means the tip can only move in this direction. Okay, we can only generate velocities in this direction. Okay, so we're losing something here, right? So if my arm is extended fully and I want to generate a velocity in this direction, I can't. I also cannot generate a velocity in this direction. Okay, so this is a singularity. This is a singularity. Okay, so the end effector loses one or more degrees of freedom of motion. All right, so that's the singularity in the case of a planar two-link open chain. Okay, we also saw an example of singularities for wrists. Okay, so as a second example, okay, let's think about this wrist here. Okay, suppose we have a wrist, 3-axis wrist, in this configuration. Okay, so here's my tool and my end effector frame. Let me use the red. Is attached this way. All right, so this is a singularity. Why is it a singularity? Well, if we want to rotate the end effector frame about the x-axis, okay, instantaneously, can we do it? No, right? We can't generate infinitesimal rotations about the x-axis here. Okay, so this is a singular configuration. This is a singularity. Okay, so can't rotate around x-hat axis. Okay. Now you remember how we found this? Okay, we wrote the Jacobian. Okay, but this time only wrote the angular velocity part, right? So this is omega is j sub theta times theta dot. Okay, and at this singular configuration, what happened to j sub theta? J sub theta, right? The rank of j sub theta dropped, okay, from 3 to 2. Okay. All right, so we want to generalize this idea to general open chains. Okay, and the way to do that is use a Jacobian. Okay, so general open chain. Okay, just write down V sub s is equal to J sub s times theta dot. Okay. And if we were to write down the columns of J sub s, let's call them, say, S1 prime, Sn prime of theta times theta dot. Okay. Then, we can write this as a linear combination, I from 1 to n of Si prime, the column, ith column, times theta I dot. Okay. All right. So if we think about this example, v1 and v2, if they span the entire xy plane, okay, it's not singular. We're okay. If they collapse, okay, if they line up, we have a singularity. Okay. So the same reasoning can be applied here. Okay. If the s primes, s1 prime up to sn prime, if they all point in sort of linearly independent directions, okay, in 6-dimensional space, then we're in good shape. It's not singular. Okay. If the dimension of that space spanned by these columns, okay, decreases by 1 or more, then we have a singularity. Okay. End effector loses 1 or more degrees of freedom. Okay, so that's what we want to find. Okay, so let's start by writing down a definition of singularity. Okay, so if rank of our Jacobian, now it depends on theta. Okay, so if at a given theta the rank of J sub s, okay, is not the maximum possible rank. Okay, so if it's less than 6, okay, is less than maximal, okay, then we say that this configuration theta, okay, theta is a singularity. Then theta is a singularity. Okay, now so some people who want call this a singular configuration. Okay, we'll go either way. Singularity. Okay, so basically we need to find the configurations theta where the rank of J drops. Okay, so in the most general case, J is usually 6 by n. Okay, so if the rank of J drops below 6, we have a singularity. Okay. Now we have to first ask ourselves, well, the definition is in terms of J sub s. What about J sub b? Okay. Okay. Question. So what about J sub b? Okay. So am I giving preferential treatment to J sub s? Okay. Well, let's think about this case. Okay. So well, first we know that J sub s is just R PR R0 times J sub b, okay, where this is the adjoint. Okay, so T is the end effector frame, so this is RP01. Okay, so we can write it this way. So the question we want to ask is, what's the rank of J sub b? Okay, is it the same as the rank of J sub s? Because if it is, then we can use either J sub b or J sub s. Okay. Okay. So rank of J sub s theta is rank of this. Okay, rank of that. Okay, now question, are the ranks of J sub S and J sub B the same? Ideally, we want it to be the same. Okay, and fortunately, they are the same. Okay, so how can we show that? Well, we're not going to do a full proof, but I'm going to give you a linear algebraic result that says, okay, so I'm going to say this is just rank of, so let's write the conclusion first. Okay, so the reason. Okay, if I have some matrix A, let's say it's n by m, okay, and P, let's say it's n by n, and let's say P is a square matrix here. Let's say P is non-singular, okay? It's invertible. Okay, so P is non-singular. So that means its rank is n. Okay, then what we have is that rank of A is equal to the rank of P times A. Okay, in other words, when you multiply any matrix by some non-singular matrix, okay, in the front or the back, it doesn't change the rank. Okay. All right, so this is a general linear algebraic result. So all we have to do is now show that this is non-singular. Okay, show that an inverse exists, a unique inverse exists. Okay, so we can show R0 PR is non-singular. Okay, easiest way, right? Just write down its inverse, okay, and show that its inverse always exists is well defined. That's one way. Other ways to show, right? How do you show a square matrix is non-singular? Well, let's call the matrix A. Okay, if you can show that the solution to AX equals 0 is uniquely x equals 0, okay, then A is non-singular. Okay. All right. So we're not going to go through all the different ways. Okay. So bottom line, doesn't matter whether I use J sub S or J sub B. Okay. I can use either to find singularities. Okay. Now, what if some guy who thinks he's pretty clever says, oh, I'm at a singularity. I know how to get rid of that singularity. I'm going to have the robot hold a broom, say. Okay, extend the arm. Okay, and that way it won't be singular. Okay, so in other words, I'm going to move the end effector to another location. So basically the idea is that, this is singular. So some guy says, oh, well, maybe I'll just have the robot hold like a long broom or something here. Okay, and I'll put the end effector here. And I'll say that's not singular. Okay, now if you think about it, it doesn't seem right, right? You can't do that. So let's show that this is nonsense. Okay, so what if end effector is relocated to another point? Okay, so if that's the case, then what we have is we now have a new location for the end effector. So let's call that T prime. T prime is what? T times some constant P, constant rigid body transformation P. Okay. So now, if we now calculate the Jacobian for this new end effector frame, okay, we can do that. Let's do T prime. Okay, so let's do T prime dot T prime inverse. Okay, is what? T dot. And now P is constant. Okay, so just P stays. And then T prime inverse is P inverse, T inverse. Okay, so this is just simply T dot T inverse. Okay, so if anybody comes to you and says, hey, I can get rid of that singularity just by moving the end effector to a different part of the robot, okay, you can say, no, you can't. Here's why. Okay, so no tricks like that. Okay, so this is the same. So if well, let's call this Vs prime. Okay, and this is V sub s. Okay, so it's the same. Okay, now this is even more nonsensical. Suppose I move the base frame of the robot, or suppose I relocate the whole robot. I pick it up, I move it here. Okay, so argument is this. So the robot is in a singular configuration. So I said, I pick the robot up, move it over here. It's in the same configuration. Is this still a singularity? Yeah, of course, right? I mean, that's so ridiculous. Like, you move the robot and say, aha, it's not a singularity. Okay, no, that's nonsense. Okay, if you wanted to show that, I mean, you do the same type of analysis. What if base is relocated? Okay, then basically now we have T prime is some P times T, okay, or P is constant. Okay, and we do the same analysis. Okay, so we'll leave that aside. All right, so I think we have enough now to start looking at some real singularities. Okay, so lessons to be learned, sort of helpful tips that we can use based on this analysis is that when we do a singularity analysis, okay, we can attach the base frame anywhere. Okay, we can also attach the end effector frame sort of anywhere. Okay, and the results won't change.